this particular ground, and the other one is the PDC. So those who would like to have the lunch of their own flavor, so they can use that coupon there, which has a certain limit. If you would like to eat more, then you have to pay for extra. Otherwise, it has certain limit. This is one thing. Second thing is that please, it is mentioned that this is today there will be a bullet intro of all the participants. So toward the end of the day, the last session is dedicated for the introduction of each of the participants so that everyone can know about everyone. So probably for the speakers and organizers, you are aware of what they are teaching, from where they are coming from. But it will give us an idea to know about you as a participant, and people can talk and discuss things with each other. So please prepare a very short introduction about you. I will give a demo, what you have to tell. So about the bullet intro, uh, what is your name? Where are you coming from? What kind of research problems you are working in? And probably you would like, if you would like to share some open problems with the audience to seek the solutions, the opinion or discussion. So you can mention them on the board. You can use the board as well. And this is the main intention of the bullet intro. So I'm just mentioning it right now so that you can prepare, you can think of collecting the details. So though this is 5 minutes to go to the talk, so we can start right now because it's already quite long break. So our first speaker is Thomas Kale, and he's going to discuss about toric ideals and applications. So over to you, Thomas.
One shot. So, can you hear me well? Hello, everyone. My name is Thomas. Thank you, Imran, and the whole team for this invitation and the opportunity to come to Pakistan. It's my first time, and to tell you something about toric ideals and their applications. So, by training, I'm an algebraist. So maybe you will notice it that I love algebra, and this is the focus of my lecture. I also like combinatorics. So doing things in algebra using combinatorics is something that I do. And when you see me here around, please feel free to approach me at any time, talk to me about your mathematics or the mathematics you see in these lectures. Yes? Okay. So my pleasure to be here. And let's start today with lecture 1 on toric ideals. So my handwriting, okay, I'll try my best to make it readable, and you'll try your best to read it. And if it doesn't match, then just let me know. I've checked out the introductory lectures that were given last week a bit, so that is a very good foundation. I will try to mimic that notation. It's also pretty standard notation. So we will often see polynomials, and they live in a polynomial ring over a field, which the polynomial ring has n generators as an algebra. So K will be any field. Sometimes we make assumptions about K when they're necessary, but not at this point. So the easiest polynomials are those that have only one term. These are monomials. And I like to write a shorthand notation. Whenever you see an x without an index, it usually means that the collection of these variables. So sometimes I write just k adjoint x. If I want to be short, I might write that, but it always means the polynomial ring with n variables. N could be 1, but n could also be n. So a monomial, I'd like to write like this in this monomial notation, x to the u, where u is a vector of exponents. So exponents of monomials are non-negative integers, n to the n. So first of all, okay, I need to make some conventions. Note, for me, 0, it's convenient that 0 is a natural number. 0 is in this set n. And this is n to the n is the tuples. So this is u1 to un in there. So I can form this monomial by taking the product 1 to n xi to the ui. Yeah, so u is the exponent vector of this monomial. And the binomial is the next best thing. That's a polynomial with at most 2 terms. So it looks like this: x to the u minus lambda x to the v. uv are now these exponent vectors, and lambda is a constant, which I do allow to be 0. I make them monic, so I will have no constant here. So that will, for all what I do, it will play no role. It's enough to have one constant here. And this constant can be 0. So if this is 0, I'm back to the case of just a monomial. So a monomial could also be, I would also call it a valid binomial. A binomial is a polynomial that has at most 2 terms. So I call a binomial unital if this lambda is either 0 or 1. Is unital if lambda equals 0 or 1. So the case of lambda equals 1 is interesting because it relates to combinatorics. So many times in mathematics, people have used binomials to do replacement systems. And this is, if you think of lambda equal 1 case, it says that x to the u minus x to the v in commutative algebra and algebraic geometry, we always think is equal to 0. That's a polynomial equation. So that means x to the u is the same as x to the v. If there's a lambda, then x to the u is lambda times x to the v. So this is a replacement rule. So binomial is a replacement rule. X to the u is the same as lambda times x to the v. I can replace x to the u by lambda x to the v. And so this is an idea that has happened in many parts of mathematics and also computer science to formulate problems by replacements of discrete objects. So let me give you a concrete example. Right there. In game theory, so there's something called combinatorial game theory. So you're talking about the positions of a combinatorial game, like which player has how many tokens of some sort. And then the rules of the game are replacements of one game position by another game position. And so sometimes you can implement these game positions as the exponents, and then the rules of the game as these binomials, and then questions about, from my current position, can I reach a winning position, can be implemented as questions in algebra, and then they become accessible to both results from theoretical computer science that tell us about the complexity of problems, and also to computer algebra that helps us to solve these problems in practice. Okay, do you want to ask a question?
Yeah, it's can be 0 or
Yes, so 0 is in n. So u could be the all 0 vector, and then to the 0 is 1. Yes, whatever is, so something x to the 0 equals 1.
1 minus lambda is binomial equals 7, right?
All right, so if I put this to 0 and this to 0, 1 minus lambda would be a binomial, and I think it doesn't hurt much. Does it hurt? Oh, okay, we can think about this corner case once I do something with them. Okay, so there are some minor issues with characteristic. I said K can be any field. So here's a fun thing. If you have X minus Y, or X1 minus X2. Sometimes when I have only few variables, I will call the variables also Y, yes? So say I have only 2. So one example, if you take X minus 1 to the P, so and P is bigger than 1, then this does not look like a binomial at all. But so you multiply it out, but if you happen to be in characteristic P, it turns out to be a binomial. So whether something is a binomial can depend on the how you represent it and what's the characteristic. So this is a binomial. So in characteristic P, because of in the US they call it freshman's dream, the dream of the beginners of studies of mathematics. So this is equal to x to the p minus y to the p. So it's binomial. So this is something that can happen. Okay, so then let's make a formal definition of a binomial ideal. An ideal, let's say I, then our polynomial ring is binomial if it has some generating set that consists of binomials. And we can also insert the adjective unitil. So I would call it a unitil ideal if it has a generating set consisting of unitil binomials, and a monomial ideal if it has a generating set consisting of monomials. So I is unitil if can be generated by unitil binomials. And a toric ideal, here's a definition that will not tell us much at the beginning. A toric ideal is a unitil ideal that's prime. Unitil ideal that is prime. Okay, so we see other descriptions that will tell us more about this. Maybe I stop writing. I cannot move up now. The bottom part is stuck. So I will stop writing here because don't want to risk any back pain. So so this toric geometry, the whole story of toric geometry could also be called log linear geometry. The idea to think about is you have some linear structure and you take e of the linear structure, exponential of the linear structure, or you have some structure where when you take the logarithm, it becomes linear. So some people call this log linear structure. For instance, in statistics, there are log linear models, and they are of this form. And so what we're going to do in this lecture is we're going to do linear algebra with these exponents, and that will give us in polynomial algebra, this will give us this toric algebra. So I also made some notes. So I have some LaTeX lecture notes. I'm working on them, and they will be available as a PDF later this week. Okay, so some of you have studied maybe Lie algebras and Lie groups. So there's an exponential map that takes the linear structure, that's the Lie algebra, to the Lie group, which is the nonlinear structure. Okay, so we study maps on exponents. Study linear maps on exponents. So a linear map will be given by a matrix. We pick bases. I will not worry about picking bases. I will just use matrices all the time. And let's say our exponents are n to the n. And I go to z to the d. I will allow integers here. Yeah. So z is the set of integers. D is some number. So such a map is given by a D times n matrix. So A is a D times n matrix with entries in the integers. Okay, I will need to sometimes specify the entries of A. I will denote this as Aij. And I don't know how it is in Pakistan. In Germany, the first index indexes the rows, the second index indexes the columns. If this is different, we have a big problem, but you're nodding. Okay, this is very good. So I will denote the rows. I will also need the rows. The rows I will index with one entry. Rows of A will be denoted A1 to A. So how many rows? Columns. So, ooh, now I will need the columns. Sorry. So columns are n columns. A1 to AN. Okay, so the image of this map, image of A, is what is called a commutative semigroup or monoid. Monoid. Okay, so basic algebra, this thing is a commutative monoid, meaning it's a set with a commutative addition that's associative, and it has a 0 element, 0, 0, 0, 0, 0, the 0 vector acts as identity. And the image has the same structure because it's a linear map. And this is denoted n times A, because it's all the linear combinations of columns of A with integer factors. U n A n U n to the n. Okay, so what we're going to do with it, we're going to define an ideal from this. Okay, so you can also think about this. So if I had to draw a picture, so it's the lattice points. Sometimes it's advantageous to think about as lattice points in a cone of RD. So let's have a concrete example. If the matrix A were to look like this, then D is 2. So I have a two-dimensional picture. This NA lives in, well, actually it lives in Z2, but N2 suffices. So the generators are 1, 0, 1, 1, and 1, 2. So this is the one direction, this is the two direction. Okay, let's make the generators in red. And then there are all these other lattice points. So this is part of, I mean, it goes on in this direction also. Sometimes I call this my favorite picture. As my favorite picture is this picture of the monoid N2. And this is how I think about the polynomial ring. So I am so much involved with the combinatorics of polynomials that I think about the polynomial ring as this picture. And you're going to see more of this picture in this week. So you have a cone in which this NA sits. And in fact, in this case, in this simple case, all of the integer points in this cone are in this set NA. So these are the generators, and then I can combine them. And it looks like, so this is, in this case, here, NA equals all integer points, the cone, and this is called a normal semigroup. It need not be the case. There can be holes. So for instance, if you double all the generators, this is a stupid way to achieve this, then there are some integer points in the cone that you don't get. Okay, so the relations among these generators. So you see there's some relations among these generators. So if you add the first generator and the third generator, if you do 1, 0 plus 1, 2, you get to 2, 2. But if you go to 1, 1 and then add 1, 1 again, you also get to 1, 2. So there's some relations. It's not a free addition. And the relations I store in the kernel of this matrix. Relations among A1 to AN. I write kernel over Z of A, because that is what it is. Relations are in the kernel, so these are M in Z to the D. So I can write it with matrix product so that AM equals 0. And if I have such a relation, I can pick it apart to make these rules that I just used as an example, right? M equals M plus minus M minus with, okay. So whenever I have such an M in Z to the D, I can decompose it as its positive part and its negative part, both of this. So this is in Z to the D, it can have negative entries, and these only have non-negative entries. And the definition is Mi plus minus. I make both definitions at the same time. Is the larger one of plus minus Mi and 0. So for M plus, I just take the larger one of Mi and 0. So that gives me Mi if Mi is non-negative and 0 otherwise. So for example, this relation there would be encoded, e.g. if I have, so what did I do? This thing once, and then minus twice the second one. That's in the kernel of this matrix. If I multiply this with this matrix on the right, I get 0. And it would be decomposed as 1, 0, 1, minus 0, 2, 0. That's something we'll do all the time. Take an integer vector and decompose it as the positive and negative part. Okay, so this map A and its kernel is the stuff that happens on the exponents. So now let's see what happens on the polynomial ring after getting some more blackboard space. Yeah.
So you have A is a map from N to Z, but then you have in the kernel M can be in the Z line.
Yeah. Okay. Yes, that's a good point. So the kernel is like a new definition. So I take this matrix, and of course I can multiply it with integer vectors. I could also put a Z here, and the map would also define a map. Is this? Can I leave it like this? Does it worry you? This is ordinary matrix multiplication, and it's some structure associated to that map, and it's not the kernel as you know it. That's why I put this Z here. But it is the kernel as you know it after you put a Z there. The good thing about the integers is that linear algebra over the integers behaves very, very similar to linear algebra over a field. So there are many important theorems in linear algebra that we learned about. And for instance, this dimension formula, that the dimension of the kernel and the dimension of the image add up to this number n, the dimension of the space where you started from. So such a formula also holds over the integers, for instance, if you define the rank appropriately. Yeah. Oh, yes. Oh, thank you. That's a problem. Yes, that should be an n. Thank you very much. Yes. Okay, so I think we have it all set up. So for polynomials, so the monoid n to the n is the exponents of k adjoint x1 to xn. So some people also write this as k adjoint n to the n for this reason. So this is more generally is like where this construction is called a monoid algebra. So this is the monoid. So it works like this. I can give you the general definition. If Q is some commutative monoid, then you can form KQ, which as a vector space, it has one dimension for each element of the monoid. N to the n has like one integer point for each monomial. And this is what the monoid algebra, you do the same. So I write it like this, direct sum over small q in big Q, elements of the monoid. And then I write one monomial, let's say t to the q, for each element of Q. So that's the one-dimensional span I will denote as K times that set, maybe. Maybe that's a notation that is possible. Now this defines it as a vector space, just one independent direct sum, one independent dimension for each monomial. And then I need to tell you what the multiplication is. And the multiplication is, of course, addition of x. So t to the q times t to the q prime equals t to the q plus q prime. So, and there you have a K algebra, a nice commutative K algebra is called the monoid algebra. And once we, maybe on Thursday, we go to this generality, and this notation comes from there. Okay, then we'll need the Laurent polynomial ring. This is the polynomial ring in which the variables are invertible. So there also exists x1 to the -1. And this is the monoid algebra for z to the d, let's say. So k adjoint z to the d. So this has exponents. This also has negative exponents. So more commonly in basic commutative algebra, this would be, let's use t variables for this. T1 plus minus 2, Td plus minus. And now from this map A, such a map A, I will get a K algebra map homomorphism that I denote phi A. Yeah, so A is as above. It's in Z to the D times N, D rows, N columns. And it goes from the polynomial ring to the Laurent polynomial ring. And it maps xj to t to the aj. Okay, let's dissect this. So this has variables x1 to xn. To tell you the map, I tell you it's a K algebra homomorphism. So it's like a linear map on the vector spaces. And I just need to tell you what happens to the generators of this. What happens to the variables in this polynomial ring? And they get mapped to, this is the monomial notation, to a product, T1. Yeah, so this, remember, this is this monomial notation. This is the product. Now I goes from 1 to D, because we have D variables, T, I, A, and now IJ comes in, right? So that's why I use the J here, so that I comes first. Okay, so maybe do the example immediately. For this example over there, let's study this map explicitly. If A is 1, 0, 1, 1, 1, 2, then phi A maps a polynomial ring with 3 variables to a Laurent polynomial ring with 2 variables, T1 plus minus T2 plus minus. So now X gets mapped to, so how do I read this? I start looking in the first column. X is the first variable. I look in the first column and I use these entries as exponents on the T. So this is T1 to the 1 and T2 to the 0. So X is mapped to T1. And Y is mapped to T1 times T2. T1 times T2. And Z is mapped to T1 times T2 squared. Okay, we'll be interested in the kernel of that map, of that K algebra homomorphism. And that's going to be a toric ideal. That's going to be the description of a toric ideal. Every toric ideal is of this form.
Beyond plus minus, it's just a simple.
So that means that t to the t1 to the -1 also exists. So that variable is invertible. It's like not many things are invertible in this ring. It's not like the function field or so. Just the variables are invertible. Yeah, 1 minus x1 is not invertible in this ring. Yeah. Why this table holds? Okay, so let's look here. For j equals 1, so I go through all the variables x1 to xn. I start with the first x1. Okay, here I named the variables x, y, z. Maybe I should, to be completely in line with the above notation, I can do it like this. So for x1, I look at A1. A1 is the first column of my matrix A. And I use the entries of A1, A11, and A21 as the exponents of the t's. So this is a product of t's, and the exponents are given by the entries of the column. So the first column is 1 and 0. Yeah, here's the first column. So I take t1 to the 1 times t2 to the 0. And t2 to the 0, I don't write. It's just 1. For the second, I get t1 to the 1, t2 to the 1. And for the third, I get t1 times t2 squared because of this 2. Okay, and the kernel of this map ought to have something to do with the kernel of this map. And that's the relation that we're going to explore. Interested in the kernel of phi A. That's an ideal in a polynomial ring, kx, or kn to the n. And in fact, it's going to be a toric ideal. Okay, so first of all, the kernel is prime. Some remarks. Kernel of phi A is prime. Now that's just putting general algebra arguments together. So this is an integral domain. Z to the D has no zero divisors. It's an integral domain. The image of this map is a subalgebra, so it's also a domain. And by the isomorphism theorem, this thing modulo kernel is isomorphic to this image, which is a domain. So that's a domain. So the kernel is a prime ideal. This is how you piece this together. Yeah.
Prime ideal is always the proper ideal of the polynomial. So
Aha. Okay. So the zeros now we can talk about the zeros in this case. Yes. Okay. So let's exclude it on my go back to my first slide and say u is always u is not equal to 0 in the for binomial. And then what can something happen with this? If A is the 0 matrix, then what happens? Everything maps to 1. Okay, so any further problems? So what's the, I think there's nothing wrong anymore. Kernel of phi A is prime. Now, the image is a domain. Kernel is prime. You think the kernel, is there some case where the kernel is not prime? No, you're good. You're good. Okay. So this is called the toric. Okay, kernel of phi A. Of phi A is throughout denoted I sub A. When A is an integer matrix, and so I sub A is called the toric ideal of A. We don't know yet that it's a toric ideal according to my definition in the beginning, but we call it the toric ideal of A. In fact, we don't know much about it. We don't know generators, for instance. So from the algebra and geometry dictionary that you have been talking about last week, algebra geometry, the dictionary, you know that the variety of IA in Kn in affine space is irreducible. And that's called the toric variety of A, affine toric variety of A. Affine toric variety of A. And what else? From this map, you get a map in the other direction. Get a map from the coordinate. So this is the coordinate ring of the algebraic torus. So if the coordinates are invertible, 0 is not a point in this space. So the map in the other direction that you get from the algebraic geometry correspondence goes from K without 0, commonly denoted K star, the algebraic torus. K star is K without 0. That's a multiplicative group. K star to the D to affine space, Kn. And the image of that has this toric variety as Zariski closure. It's in fact dense in the in this variety. Okay. Yeah, so this maps T1 to the TD to these coordinates T to the A1 to T to the AN. So we might hear more about this in some other lectures this week. Okay, so in classical, just a remark, in classical algebraic geometry, when you hear the name toric variety, it often refers to projective geometry. I will have a remark about this in the end, but until when you read the book of Fulton, if you type toric varieties into Google, it will say, oh, why don't you read the book of Fulton from the 90s? And back then, toric ideal included the case that the coordinate ring is normal. I think by now this assumption has been dropped. So there is somehow a bit, yeah, the literature is a bit split. The older literature, when they say toric variety, they assume it's a normal variety. And I will not define normal. It means something that the singularities of the variety of a certain mild kind that allow you to do a theory of divisors on that variety. But I think I've heard the story that there was an Oberwolfach meeting where all the experts gathered and decided that to drop this normal assumption. So by now, a toric variety is a variety of a toric ideal without any normality assumption. But in the old books, this is still the assumption. Okay, so in our 1-1-2 example, how can we get anything about this kernel? Well, we can observe that each element of this integer kernel of kernel Z of A gives us something in the kernel of phi A, namely a binomial, gives a binomial in the kernel of phi A in this algebra map. So let's look at this in our little example first. So we had for A that we have 1 minus 2, 1 is in this integer kernel. And this means, so these are the images are T1 times this, T0 times this. So if I have addition here corresponds to multiplication of monomials. This is like this log linear story. So if this plus this equals twice this, then the generator corresponding to this thing times the generator corresponding to this thing is the square of this. Or let me tell you something that you already know. T1 times, which is the first generator, T1, T2 squared is the same as T1 times T2 squared. Looks trivial, but it tells us that in this kernel, x1 times x3 minus x2 squared is in the kernel of phi a. Okay? x1 maps to this, x3 maps to this. If I multiply them together, I have to add exponents. x2 squared maps to this square here. And if these are if the addition of exponents tells me how to form these binomials in the kernel. So in this example, a very nice and special situation holds. So we have the dimension formula. I don't know what's I think in English it's called the rank nullity theorem, linear algebra. Yeah, rank nullity. I always call it dimension formula because in German it's called Dimensionsformel. So dimension formula, rank nullity holds in z to the d, z to the n 2. So the rank of this matrix is 2. Rank of A is equal to 2. So the rank of kernel of A is equal to 1. And in this special case, this ideal IA is generated by this one binomial, x1, x3 minus x2 squared. And this is a lucky coincidence. In general, the generators of IA are, well, should I write mysterious? No, I write not easy to find. And in particular, very important, you might need more than rank many. In particular, more than rank of kernel may be necessary. So maybe that's a computation we can do in the tutorial. Maybe I can. Let's see how we're doing. Okay, I will mention this example, and then in the tutorial, I will show you how to do this on a larger scale using a computer. So the example, you can do a D2 n equals 4 example, where this happens. I tell you the matrix 1, 5, 1, 4, 1, 2, 1, 1. And then the kernel, we do our rank nullity theorem as an integer lattice. It's generated by 2, the kernel of A. Rank of kernel of A is 2. And I mean, 2 generators, you can make generators by, okay, you want to write this in terms of others. So let's see. I'll just look at my solution. Okay, you take 3 times this and add it to this. So here 2 generators. 1, 0, minus 4, 3. And if you take the second one, you just take minus 3, 2. But IA needs 4 generators. Okay, so let me make another remark about minimal generators. So in this In the linear algebra case, we are in the nice situation. It's like well defined. The rank of the kernel is the number of generators you need for this kernel. In commutative algebra, minimal number of generators of an ideal is not well defined unless you have this Nakayama lemma. So in the homogeneous setting, if the kernel is homogeneous, then you can have, then there are Betti numbers, and you have this notion of how many generators are necessary to generate this ideal. It doesn't depend on the generating set. There is a minimal number of generators, and from each generating set, you can compute it. And if it's not homogeneous, this is not the case. So it asks the question, when is this IA homogeneous? And the answer to this is, note, if the all ones vector, 1, 1, 1, 1, 1, 1, or a multiple of it, let's say K is already used, S times this vector, is in the row space of A. So let's forget about the S. Yeah, S is some natural number. So let's say the all ones vector is in the row space, then something in the kernel of this matrix will have the property that all ones times the thing in the kernel is 0. So then the number of the sum of the positive entries and the sum of the negative entries is equal. Now these become the exponents of the binomials. Like in this case, 1 plus 1 equals 2. So this is the reason why this is a homogeneous quadratic binomial. Yeah. So the sum of the positive entries equals the sum of the negative entries. So that implies that IA is homogeneous, or that the norm, what is it? The one norm, if you just add up the entries, I take the one norm of M plus equals the one norm of M minus for M in this integer kernel. Okay, so it can happen, and you might be interested in these generators. So, but it's it's not a complicated computer algebra computation. I will show you in the tutorial some ways to input a matrix and get out the generators of the ideal. Yeah, so that's a problem that's solved and implemented. For a while, this has been a kind of sport to take all kinds of matrices that you know, for instance, from combinatorial optimization, or 0-1 matrices that are incidence matrices of all sorts of combinatorial structures, matroids, simplicial complexes, and compute the generators of the toric ideal and ask the question, what kind of properties of the generators, e.g. degree, can you predict from the combinatorics of this matrix? Yeah, so understanding this map that inputs a matrix and outputs the generators of this toric ideal is a combinatorial procedure. And out of this, like, there was a time when a lot of data was generated. Many people were investigating this in big classes of examples. For instance, there's this website called, well, I talk about this website later. And but new algebra theorems have been discovered. So sometimes you can have some combinatorial procedure. So imagine there's a map that takes a graph. From the graph, it makes this matrix. Doesn't matter now how it does this. And then you get a toric ideal. And you observe that if the graph has certain properties, for instance, it's colorable or it's K minor 3 or something, then this ideal is generated in degree at most 4. So we want to prove such a theorem. And the way you can prove such a theorem sometimes is you use properties of the graph. If it's K4 minor 3, it has a certain decomposition into subgraphs. And you study how this decomposition into subgraphs looks on the matrices and therefore looks on the ideals. And if you're very lucky, like Seth Sullivan was in 15 years ago, you discover a new type of algebraic construction. This is now called the toric fiber products. Yeah. So this is somehow new insights in algebra can happen from studying this kind of maps from combinatorics to algebra, because it gives you a new way of describing things. Okay, I can say more about this later. So now we want to see some properties of this toric ideal. So what I've done so far is only I've told you some of the generators, but we don't even know that IA is a binomial ideal to start with. Why can every polynomial in this kernel be written in terms of these binomials? So let's figure that out. Turns out all generators of IA are of this form. And by this form, I mean x to the m plus minus x to the m minus for some m equals m plus minus m minus in the kernel of the matrix A, in the integer kernel. And this is what I've been doing here. I've been taking this vector, decomposing it into 1, 1, 1, 0, 1, which is this, minus the negative part 0, 2, 0, which gives this. Yeah? So through this chain, I've been doing exactly this. Yeah, okay. But turns out IA can be generated by binomials of this form. I want to avoid the term minimal generators because this applies also to the setting where minimal generators is not defined. Okay, so let's say we have a lemma or proposition. I tell you something stronger. IA as a K vector space is generated all the binomials of the form x to the u minus x to the v such that a times u equals a times v. And uv are arbitrary exponent vectors. Okay, first some remarks before we get an idea of the proof. This is the same as this is equivalent to all the polynomials of the form x to the m plus minus x to the m minus for a times m equal to 0, m in z to the n, because a m equals a m plus minus m minus. So a m equal to 0 is equivalent to a m plus minus a equal to a m minus. So there are two ways to write it, and either you take the non-negative exponents and then you want them to be mapped to the same under A, or you take you can always, as it turns out, put these together safely and write this exponent. So small consistency check if you want. So let's say u equals 1, 1, 1 and v equals 2, 0, 1. So this would translate to the binomial x 1, x2, x3 minus x1 squared x3. So I can factor this is x1 times x3 times x2 minus x1. So exactly because the supports of these were not disjoint, I get this factorization. But if I see this in a prime ideal, I know that either this is in the prime ideal or this is in the prime ideal. Turns out no monomials are in the prime ideal, except if variables map to 0. And it suffices to consider these supports that are disjoint. Yeah? So these cases are in fact equivalent. Okay, so in general, what does this generate as a k-vector space? This is much stronger. So generate as k-vector space implies also generate as ideal, because generate as a k-vector space, you do k linear combinations, and for ideal, you can do polynomial combinations. And of course, they are not a basis, so they're even dependent over k. There are way too many, there are infinitely many, but because this is a Noetherian ring, you have this general principle that from this set, you can select a finite generating set from this infinite generating set, because k x1 to xn is Noetherian. This means a finite subset generates IA. So this implies that IA is toric, according to my definition, because these are unital binomials, and we know from this other short argument that it's prime. Okay, so the proof sketch or idea. So there are many proofs. There are several proofs of this around. Some of them are wrong. So the idea is you want to have an F. There's one idea that doesn't work really well, but it's instructive. If you have an F in the kernel of A, in the kernel of phi A, and you want to show that it can be expressed as a linear combination of such binomials. This is what it says here, as a k linear combination. So every polynomial in the kernel can be written with these binomials by summing them with k coefficients. Okay, so if you have this F, you take its lead term in some term order, take lead term x to the u in some term order. So now you apply, think of F, yeah? So F is x to the u plus other terms. So now you apply this map, phi A of F is equal to phi A of x to the u plus phi A of the rest. And now this is equal to 0. So now you have to, this here gives you t to the a times u. Yeah, you know the map of, okay, this is u on top. You know the map of monomials, yeah, on monomials. Okay, so this is also small note, part of the practice with the notation. If you take phi A of x to the u, it equals a times t to the a times u. Yeah, if you take just one, it gets t to the column. If you square it, it gives you twice the column. And if you take an arbitrary u, it gives you exactly the linear combination in the exponent, the linear combination of columns, which we write as this matrix product. Okay, anyway, here you get this thing, t to the a to the u, but because it's 0, somewhere in this part, hiding is something that cancels this. Some term where there appears t to the same thing. Okay, so I can find another term which cancels this, So I can subtract from f such a binomial and make a polynomial with the smaller lead term. So then you do the standard Gröbner contradiction argument. So you say, okay, among all the f's that cannot be written with these binomials, you take one with the smallest lead term, then you subtract one of these binomials, then it has a smaller lead term, and it still cannot be written by this binomial, so you get a contradiction. So now I cheated because this proof doesn't work. Why does this proof not work? Because there could be a coefficient here. And so you could have to collect these things. So you have to be more careful, because if this t to the au could be cancelled by half t to the av and then half t to the av prime. Yes, so you have to keep track of this kind of stuff. And it's annoying to keep track of this kind of stuff. That's why I have an abstract dimension argument, which tells you nothing. So there's in this lecture, there's an abstract dimension argument. You just compare dimensions of the two sides and take the isomorphism theorem from linear algebra. Okay, so should be almost done. Yes, so I have not finished the characterization. So I said that toric ideal is defined as unital binomial prime ideal, and I've shown you that this toric ideal of A is such an ideal. But why is every unital binomial ideal of this form? You have to be a bit more careful. And this is part of a theorem of Eisenbart and Sturmfeld, one could say. Or there's a more general theorem that implies this. So let's say every unital binomial prime ideal, let's say that does not contain variables. Okay, monomial prime ideal is also binomial prime ideal. Let's leave these out. Is of the form IA for some A. And this is part of theorem of Eisenbart and Sturmfeld. And I'm not going to prove this, but I'm going to show you how to get the A. Yeah, so let's finish by telling you how to get the A. The A matrix can be reconstructed. Basically, you reverse this procedure. The kernel of A, so how do you make this procedure? You take A, you compute the kernel. From the kernel, you get the generators, but you need more. We don't really know how to make a computer program that computes the generators. We just know these binomial properties. But the reverse procedure is from the exponents. So if x to the m plus minus x to the m minus, I for m1 to m, let's say we have s generators, ms generates IA, generates I, then let L be the lattice in Z to the, where are we? Z to the N with generators M1 to the MS, and then compute min-gens, compute minimal generators of L, let's say M1 to the MS prime, make a matrix, let L be the matrix that has these S columns, M1 to MS prime. And then you compute the Smith normal form. The normal form, Smith normal form, one of these normal forms. Smith normal form is this diagonalization that changes bases in both lattices. Yeah, you change bases in the lattice in both lattices, and then you can always get a diagonal form with no constrictions, no restrictions whatsoever. So this means you write a product S, L, T, ST invertible, so that it looks like this, diagonal and then zeros. So this is actually, I mean, it looks wrong, but this is like a long times short matrix. Yeah. So this is sublattice of Z to the N. It has N or fewer generators. So it's like this is short and this is long. So this matrix looks like this, is diagonal. If this is a toric ideal, the diagonals are actually going to be ones. Doesn't matter here. And now in this S matrix, because this is an invertible matrix, which does column operations, in this S matrix, you subdivide the S matrix into the upper part, which corresponds to this, you throw away. And the lower part of the S matrix is a matrix so that this lower part times L gives 0. So it's an A matrix. I will show this in the tutorial and maybe stop here. Okay, let's just take this one note to be continued with the computer. Lower part of A of S is a matrix A such that L equals integer kernel of A. Okay, so fortunately I started 5 minutes early and I can finish on time. Thanks.
Are there any questions from the audience? Yeah. So I think this is just a small typo at the top right, when you are making the assumption on the ideal. Does not contain any. Sorry.
Variables.
There.
So here's a binomial prime ideal. So the ideal X, according to my definitions, would be a binomial prime ideal, because just this monomial, this is just for X1, and this I need to exclude for this other direction. So this is not of the form kernel of phi A, this monomial ideal.
So do you mean they don't contain monomials? Just no monomials in the ideal, right?
If a prime ideal contains a monomial, it also contains all the variables that make that monomial. So that's that's why I can write variables there. Yeah.
When A is the zero matrix,
Yeah.
then the kernel is whole ZD. Okay.
Yes. Okay. So
But
let's.
the kernel of P of A is not the whole ring.
Yeah. So let's exclude. Let's say A is of full rank and D is at least 1. So all this, everything I've been doing. So we have been working with the kernel of A. So it depends only on the row space of A. If the row space of A is unchanged, if you do row operations on A, nothing changes about the ideal, because the ideal is computed from the kernel. And so this matrix is not unique. You can see this here. I'm here in this procedure, I'm producing some matrix A that has this L as a kernel, but there are many choices. So I can do row operate. It's only the row space of A actually counts. So, and if that row space is 0, then some of the things don't work. So let's exclude that case by saying the rank of A is at least 1.
Okay. Are there any other questions? Are there questions from IBA side? Okay, if this is the case, let us thank the speaker. Thank you, Tom. Thank you. Now, next speaker is Carlos. Carlos Amendola.
There's one more.